So this is going to be about the third chapter of the probability section, section 4 of our stats, and this is going to be about the addition rule. So there's an addition rule and there's a multiplication rule in probability that deals with addition, multiplication, respectively. So we're going to focus on the addition one today. And so, a few definitions here. Again, we talked about this last time, but a compound event is an event that has two or more simple events going on. So, for example, flipping a coin to try to get tails and rolling a die to try to get a 1. That would be a compound event. What's the chance that you get tails and roll a 1? Because that's made up of two simple events. Flipping a coin, simple event. Rolling a die, simple event. So if you want the chance of something happening that involves both of them, that's a compound event. And there's two sort of versions of this. There's the inclusive and the exclusive version. So the inclusive version is when either event can occur or both events can occur. So for example, rolling a die and flipping a coin would be an inclusive type of event, because if I ask you what's the probability of rolling a 1 and flipping tails, those can both happen at the same time. I can flip a tails, I can roll a 1, or I can do them both. So I might get tails and 1, I might get tails and 6, I might get 1 and heads. So I can either have 1, both, or none of them occur. That's the inclusive rule. Exclusive are when events are either called mutually exclusive or disjoint. So for example, this would be like if I flip a coin and roll a die, I ask you what's the chance of flipping heads and tails? Well, that can't happen. You can't flip heads and tails, and then you can say roll a 1. So what's the chance that you flip a heads and tails and roll a 1? Well, again, that can't happen. That's those two events, flipping heads and tails itself, cannot happen at the same time. So they are mutually exclusive events. So flipping heads and flipping tails are mutually exclusive because they both cannot happen at the same time. So usually we're going to be focusing on the inclusive part, but we will talk about mutually exclusive events a little bit as well. And there's a difference between and or. So if I say what's the chance that you flip a heads and roll a 1 versus what's the chance that you flip a heads or roll a 1, and we'll talk about that a little bit later too. And by later I mean now. So the or and the and version. So the or means that the first event occurs and the second does not. The second event occurs and the first does not, or that they both occur at the same time. So once again, going back to my coin and die example, flipping a heads or rolling a tails. So I want all the possible cases where I flip heads, all the possible cases where I should say flip a heads and roll a 1. All the possible cases where I flip heads, all the possible cases where I roll 1, and all the possible cases where they both happen. If I say I want the probability of flipping heads and rolling a 1, then I want just the cases where they both happen. So and means that both must occur, or means that at least one can occur. So they can both occur, but as long as one occur, we're going to count it as a success. So and is a little bit more strict than or. So again, if it's not implied, we usually talk about or, but just be careful of the wording of the question there. And again, we're talking about one single event here. So we're talking about something that's happening at the same time. And again, that will make more clear when we get to an example here. So this is the formal addition rule. This is like what it says in math terms. So the probability of A or B is the probability of A plus the probability of B happening minus the probability of them both happening. And again, the reason we do a minus here is because these are all the cases where A happens and all the cases where A and B happens. So this one right here, if I go to my little pen here, come on. So this one right here includes the case of A and B. That's included in that probability. And here, this also includes the case of A and B, because that's a case where B happens as well. So this event here is double counted. It's counted in this probability and it's counted in this probability. So we have to subtract it off because we don't want to double count. That's why we subtract that case there. So for example, if I said I want to flip a tails and roll a 1, what's the probability of flipping a tails? Well, the probability of flipping tails what's some sample spaces here? So I could go tails and 1, and that would account for probability of flipping tails, or that would also count for probability of rolling a 1. So flipping a tails and rolling a 1 would be counted in both of these probabilities, so I have to subtract it off itself to make sure I don't count that one twice in my calculations. The intuitive rule is just saying what this is in words, so this is just the English version of what this says. And again, let's go ahead and the reason I say intuitive rule is that some people call it that. I'll show you that they're exactly the same thing here in this next example. So let's talk about drug testing here. So let's say we're a company, we're testing our employees, and we get the following results there. So we have, or let's say you're just analyzing to see if a test is useful. So you're drug testing some people. These people were true positive, which means they tested positive and they used drugs. You know they used drugs. They either told you or you found out. These people tested positive but did not use drugs. So these are the, excuse me, had a hiccup there. These are the false positives. So these are people that tested positive, but you know for a fact they did not use drugs. These people were false negatives in that they tested negative, but they did use drugs, and these were true negatives because, again, they tested negative and they did not use drugs. So this is the breakdown of our results here. We want the probability that if we pick an employee at random or a person at random, what's the probability that the person had a positive test or used drugs? So we want either one. So we'll call this my probability A, positive test. B would be using drugs. So number of people who had a positive test. So how many people had a positive test? Well, both of these sets of people had positive tests. Now this set of people didn't use drugs, but they still had a positive test. They still count for that picking a person that had a positive test item. So this would be 119 plus 24. So if we do that, 119 plus 24 here, just make sure I don't mess up on my numbers here, we get 143. So 143 people had a positive test. How many people used drugs? Well, these people right here, this set of people are the one, whoops, wrong one. My bad. I really hate that when that happens. So these people, 119 plus 24, those people had a positive test, and these people here are the ones that use drugs. So 119 and 3, both of these sets of people use drugs. Now these people tested negative, but they still use drugs. They still fall into that second category there. So 119 plus 3, that would end up being, whoops, 122, duh. Not sure why I typed that in there. 122. Now we have 300 people total, so 300 people total took the test. I want the probability that a person tested positive or used drugs. Okay, well I know it's going to be out of 300. So I have 143 people tested positive, so that's the probability of A. And this one's going to be out of 300 too. I had 122 people who used drugs. Now the problem with that is that if you notice here, I used the 119 twice. The 119 is counted for in this probability, that 143, and the 119 is counted for in this 122 here. So I'm going to subtract off 119 over 300 because that's double counted. So this is where I get probability of A, probability of B, minus the probability of both of them together. So this is obviously going to be something out of 300. But that's where that subtraction comes into play, because again, in this case, you double count the 119, so you have to subtract that off at the end, otherwise you're going to overestimate your stuff there. So this would end up being 146 out of 300 people, which if we do that to get a decimal, is about a 49% chance. So 0.486 repeating, which is roughly a 49% chance if you round it to the nearest whole number, which we probably shouldn't. We should probably do 48.6, but oh well. So that's what we mean by that subtraction bitting, and that always throws people off, is why you need to subtract. That's why, because you're double counting a number, in this case the 119. Now the formal rule is the exact same thing. You go through the exact same process. Number of people who had a positive test, well, 143. Number of people who use drugs, well, 122. Number of people who used drugs and had a positive test, well, 119. And then again, you set up the same way. So there's really no difference between the formal and the intuitive rule. It's the same exact thing. Probability of A is this fraction. Probability of B is that fraction. Probability of A and B is that fraction. In fact, if you want to, you can just leave off the fraction. Just do 143 plus 122 minus 19 and get your number, and then just divide that by the total number of people, which in this case is 300. But I just prefer to keep everything as a fraction just to make sure I'm consistent. But that's the idea here about how to use this addition and intuitive rule and stuff like that. You just simply account for each case individually and then subtract off the case where they both happen. And again, this is when we're using an OR example. So this is when we want A or B or both. If it said AND, so if this OR was changed to an AND, then the only number I would use is 119. My answer would simply be 119 out of 300. That's the probability of A and B. If I want OR, that's where I have to do this little formal rule here, or this intuitive rule here, to actually get the OR version of it. Now, we talked a little bit about mutual exclusivity in the beginning here. So A and B are mutually exclusive, or sometimes called disjoint, same thing, if they cannot occur at the same time. So for example, testing positive and not using drugs are not mutually exclusive. You can test positive and have not used drugs. These people did it right here. These people tested positive and did not use drugs. So these events are not mutually exclusive. Now, what if I said testing positive and testing negative? Well, those are mutually exclusive because they cannot happen at the same time. I cannot have one person test both positive and negative. So mutually exclusive events are events where if you take a single trial, you will not see both happen in that one trial. You might, if you do 10 trials, you might see them pop up every now and then, but in any single trial, you will not see both events happening if they're mutually exclusive. Like again, testing positive and testing negative. So let's try another example here that's a little bit more numeric. So let's say we have a 2 die, and we're rolling both of them, and we want the probability of rolling a 6 or a 5 exactly once. So what happens here is we roll the first die, write down the number, roll the second die, write down the number, and we want the probability that in that case we have a 6 or 5 exactly once. Okay? So that means basically we don't want 66 or 55. That essentially we're looking for that. So what are the total possible ways that this can happen? Well, we have this list here. These are all the possible ways that the results can happen. So you can roll a 1 and roll a 1. You can roll a 1 and roll a 2. You can roll a 1 and roll a 3, so on and so forth. So we're not adding the numbers together. We're just putting them side by side. So what's the probability of rolling a 6 or 5 exactly once? Well, what's the probability of rolling a 6 once? So if we roll the die, what's the probability that we get a 6 once? So this one right here, 16 works because that's a 6 once. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We do not include 66 because we want it just once. So it'd be 10 ways that we can roll a 6 once. And I have a sneaking suspicion that 5 is going to be the same way, but let's just check here. So what are the ways that we can roll a 5 once? Well, there's 1, 2, 3, 4, 5, 6, 7, 8. We don't want 55 because that happens twice. And 10. So there's 10 ways we can roll a 5 once. Now, what's the probability that they both happen? So basically, again, what's the probability that, what's the double counted version? Well, that one is this one right here. Let me get that color here. This one right here, if you notice, is counted twice. It's counted both in the 6 and it's counted both in the 5. So the probability of it happening is just 1. So there's one case where both 6 and 5 occur once. In fact, actually, I missed one, didn't I? Yep, I did. Always check your work, folks. So there's actually 2 cases where that happens because it happens right here too. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 ways, but I forgot to mark down the 10th one. That's why it threw me off there. So there's actually 2 ways it happens once because this one also has the 6 and 5 happening. So this is actually 2. Intentional mistake as always, right? So 10 ways that 6 can happen once. 5 ways, or 10 ways that 5 can happen once, and 2 ways where they both happen once. So again, I don't want to double count these numbers. So when I set this up, the probability that 6 happens once, well, that's going to be 10 out of 36, plus the probability that 5 happens once, so that's going to be 10 out of 36, minus the probability that they both happen once, well, that's going to be 2 out of 36. So basically, this subtracts off my double count of 65 and 56, and I'm going to erase that line there. 6. There we go. So if we add this together, that'd be 20 minus 2 would be 18 out of 36, which simplifies down to 1/2, right? Just making sure I did my calculations there right. Right, yeah. So that's going to be the probability of getting a 6 or 5 exactly once. Again, if you want to, you can do it in the more intuitive way, which is just saying, okay, 10 ways the first can happen, 10 ways the second can happen, 2 ways they both happen. That's 18, and then do 18 out of 36 gets you 1/2. So same way here, it's just that you hold off the fraction until the very end, because the fraction really doesn't mean much until the very end. But again, to each his own. So listing out the ways that stuff can happen can help you out. So whether it's a list like this or whether it's a table like we had over here, listing it out as a table. This helps you identify where the double count occurs and can help you structure your values there. So if you don't have a table with you to have this here, I really suggest making your own table like this or making your own list like, come on, there you go, like this, so that, again, you have a better visual on things. So one more example here. What is the probability that when rolling 2 fair die, so you're rolling 2 dice, you roll a sum that is a perfect square, or you roll a sum that's bigger than or equal to 8. So here we have a list of outcomes here. This is another way you can kind of list your outcomes, is instead of doing it like a normal table, you have all the possible ways the first die can happen, all the possible ways the second die can happen, and then since you're summing them together, you just write out a table of sums. So again, you make your table sort of an arithmetic table rather than a normal, 2x4 table. Anyway, we want a sum that's a perfect square or a sum that's bigger than or equal to 8. So if we have a table like this, instead of doing it the formal way, let's do it the more intuitive way, which is simply just counting up every possibility that fits. So let's count up all the sums that are perfect squares. So all the sums that are perfect squares. Remember, a perfect square is a number that if you square root it, you get a whole number back. So these are all perfect squares here. 4 is a perfect square, and 9 is a perfect square. And that's about it. 9 and 4 are the only perfect squares. And we also say, or roll a sum that's bigger than or equal to 8. Well, 8 is obviously bigger than or equal to 8, so all of these count. Normally we'd circle 9, but we already have those circles, so let's avoid double counting right off the bat and just leave it like that. And then all of these count as well. 10, 11, 12, those are all bigger than 8 too. And that's about it. So we have a total of 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have a total of 36 outcomes. Not all of them are unique, but there's 36 different ways that this can happen because it's a 6x6 table. Come on, there we go. So 36 possible outcomes, of which we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have 18 possible outcomes that we want, which are perfect squares or that we roll bigger than or equal to 8. And again, notice that we avoid double counting the 9s as being a perfect square and bigger than or equal to 8. And this will end up being 1/2 again. So there's half of those sums there are either perfect squares or bigger than or equal to 8. So once again, making a table or a visual of your list of outcomes, excuse me, can help you, again, visualize your answer, because it's a lot easier to count this up rather than doing it all in your head. So last little thing here are just some notation tricks. So sometimes in a more formal setting, instead of saying the word or, they'll put this little U here, or instead of saying the word and, they'll put this little upside down U here, and that's just the formal notation of and or. So this symbol right here means A or B. This symbol right here means A and B. This is sometimes called the union and the intersection rather than the and or version. So an or is called a U or is called a union, and is the upside down U or called the intersection. But they mean the exact same thing. Nothing changes calculation wise. It's just that some people use this notation than the and or notation. In a Venn diagram, it kind of looks like this. So these are all the cases where A and B happens, which is why it's called the intersection, because if you made a list of all the possible outcomes for A, made a list of all the possible outcomes for B, the points where they quote unquote cross or intersect would be the points of A and B. So that's why we get the name intersection from. So for example, a single card is chosen from a random 52 card deck. What's the probability that we choose a king or a club? So this would be written as this: the probability that we choose a king or, so a union, club. So that would be how you would write that. Rather than saying king or club, you would say king and then union club. And again, you'd solve this the exact same way you did the other ones. So what's the probability that you draw a king? Well, there's 4 kings out of 52 cards. So 4 out of 52. What's the probability that you draw a club? Well, there's 13 clubs out of 52 cards. And then what's the probability that you draw a king and a club? Well, there's only 1 king of clubs, so 1 out of 52. And then this answer here, whatever you get when you add them up, would be your answer. So this would end up being what, 16 out of 52? Which would be whatever fraction that is. So it's solved the exact same way. It's just, again, sometimes you'll see this notation rather than the and or the or. Come on. There we go. So the last thing here is, once again, just reiterating these ideas of complementary events. Can't talk today. So remember, a complementary event is an event that does not happen. So the complement of A is the probability that A does not occur. Now the thing about this is that these are mutually exclusive. So the complement is always mutually exclusive to its original event. So you cannot have, like if I say flipping a coin, you can't have a case where you both flip a tails and not flip a tails. Those are mutually exclusive events. They can both not happen at the same time, which is why they have this little setup here, where if you want the complement of an event, you simply take everything, or 1, because that stands for 100%, minus the chance that it does happen. So if you take 1 minus the chance it does happen, you're left with the chance that it doesn't. And vice versa. If you take 1 minus the chance that an event does not happen, you get the chance that it does happen. So here, we do it with a boy or a girl. So globally, it's not actually a 50-50 chance. The chance of you having a boy is about a 51% chance, 0.512. So if you want the chance that you have a girl, you simply take 1 minus the chance that you have a boy, which would be 1 minus 0.512, which gives you about a 48% or 48.8% chance of having a girl. So again, there's really nothing really new here. We talked about this a lot, but I want to keep emphasizing this point because, like I said, it's going to help us later on in the course of having this idea of complementary events and being able to use that to help us solve more complex probability problems. So just remember, a complementary event is 1 minus the chance that the event happens, and vice versa. That's it. So that's all for this video. Again, and or are very slightly different, but they overall have the same sort of idea behind them. So let me email me if you have any questions. Hope you enjoy the video. A little bit spacey today, I know, but I think we did an okay job. So again, let me know if you need any more clarification. Otherwise, have a good day, night, or afternoon.